Okay, so let's start again. Good morning to everybody. And the first talk of this morning is by Enrico Franchi, who's a very well-known Pythonista in Italia. And he's going to talk about how to improve performance and get much optimization for beginners. Thank you.
So, first thing, Python is not slow, it's differently fast. And in fact, just to give some ideas, I believe that often memory usage is my main problem, and it's a real problem, in the sense that usually CPU-bound performance can be adequate, especially if you use, for example, NumPy for numerical computations or something like that. And I also tend to favor algorithmic or architecture optimization rather than low-level optimization, micro-optimization, that kind of stuff, which usually doesn't work unless you're really very close to what you want to obtain. Second thing to say is that many issues can be just solved by using PyPy. However, in many situations we can't do that, and CPython is the standard. We cannot afford to use something different, which is a pity, in fact, but still it's what we have to live with. So this is the rough outline of the presentation. I'll introduce the basic types of Python, especially regarding memory occupation and some implementation details. We're talking about C-level stuff here. Then I'll give some hints about object-oriented design in scientific settings, which may be quite different from what you would consider a good object-oriented design. And then we end the whole thing with CPU and memory profiling. Why profiling? Because you just can't fly blind and hope to get the spot of your program that is the actual problem. So unless you know how to identify the problem, you cannot fix it. Okay? Unless you just switch to PyPy, which may work. Low-level languages are great sometimes. Sometimes not, and much of us prefer high-level languages. Maybe. I don't know, we are at a Python conference, so. And what's the problem? Low-level languages are easy to understand in the sense that they provide a very low-level abstraction over the machine, and it's somewhat, there is less detail is hidden, okay? In fact, high-level languages, we use them because we want the abstraction they provide, which is usually fine unless when it is not, which seems a bit obvious, but still, when you have performance issues on a high-level language, you may have to understand quite a lot more about how your platform works, and since you have some details, some more details, some more code to understand, this may be a little bit more troublesome. So this is a place where we can see something like an abstraction leak, not in the sense of the interface, not in the sense of errors, but we see that things are just not as fast as we expect them to be, and we understand that something beneath the lid is behaving differently from what we actually expected. The other thing is that we have been led to think that object-oriented programming is just the solution to every problem. But the problem is that object-oriented solution leads toward nested structures. We want to create objects, and these objects have attributes, and these attributes are objects that have attributes, and so on. And all this has a cost, as we will be saying in a few slides. So sometimes when you want to get fast, you have to flatten your design and just reduce the abstraction of your code, or at least not use too many layers. Just one layer, probably, because you don't want to be too low level. Okay. So, object-oriented programming is mostly stateful, at least in most conception of object-oriented programming. And for example, a way to deal with mutability is encapsulation, which also helps to hide the implementation details. So there are these mantras here, programmed to an interface, not to an implementation. So you want to create an abstract interface, not in the sense of Java interfaces, but something logical here, okay? And you don't want to actually have the implementation detail make your code more complex. And the other thing, this was the title of a recipe in a famous C++ book, is avoid returning handlers to object internals. Because of course, when you do that, everybody can modify the guts of your objects, and you have something like distance action. Something happens far from where the object is, and you may not understand that, and it's difficult to debug. So creating interfaces that provide computationally efficient operation and all the required operations, because we don't want to leak details, is not easy, because we can just make the beautiful designs sometimes, okay? So for example, consider this is a point. We have just a simple constructor here and two attributes. Of course we would be implementing all the methods, plus and str and all that, but it's not important now. The thing is that this takes a lot of memory. We'll be seeing that in a few slides, especially if you want to have a lot of points in your code, which probably you do, otherwise you won't be defining this thing if you just use it from time to time. The second thing is that I expect a point to behave more like a number, not like a list, okay? So I expect a point to be immutable. I don't change points, okay? The origin is the origin. It doesn't go around the plane, okay? If you want a point that is not the origin, that is a different point. So there is an identity problem, okay? You don't want a mutable object here, absolutely. That is like number. You don't want to assign 4 to 3 and 3 becomes 4 in your code, which was something that used to happen some 40 years ago in some languages, okay? So this is better actually. We just use a named tuple, okay? And we also have some more functionality provided by the named tuple thing, like this beautiful str rep, whatever it is, method that allows us to see the actual contents of the point. And this also contains less code, uses less memory. So if you get just the size of this point, it's 72 bytes. And if we measure the actual size of the infrastructure needed for this, it's 344 bytes. We are not measuring the actual memory used by the integers here, 3 and 4. That's outside both numbers, okay? But that is the idea. So if you have 1,000 points, this against this is interesting. If you have 1,000,000, then you start having a problem if you use this thing, okay? Plus there is the whole wrong semantics that this has and this hasn't. Of course you can give the right semantics to this, but it's some more effort, so just use this, please. The second thing is related to the point example. Okay, here I should have used the good implementation, but still. Imagine you want to create a triangle. You have this class, because you have a lot of triangles. And you may be tempted to do something like this. So you have vertices in a list, for example, and you return the list, maybe because you don't want to provide a draw method to the shape interface. but you want to be able to draw them, okay? So you just provide a line, a list of points that may be a decent interface for drawing, provided that you know how to draw a line, for example. Still, these things is a very big problem, because actually we are returning a handle. And if we do this, we have very few advantages over a plain list. We just use more memory. I'm not saying that using a plain list to represent a triangle is a good design. I'm just saying that this is just as bad. So, if you want a bad design, at least take the one that occupies less memory. Okay? If you want a good design, well, we can do something smarter here. For example, we can make a copy. If we make a copy of the list, the main problem goes away. What is the main problem? The main problem is that you can access the guts of the object, which is a mutable list, and somewhere in the code, maybe you are making some manipulation, and you modify this list, because you lost track that this list actually is an alias. The list you are modifying is actually an alias for a list that is in the guts of a triangle object. Okay? So we have a problem. Instead, if we make a copy, then we have no problem anymore, because you modify the copy and not the original list. The problem is that we are paying the performance of the copy, which is probably not much for a small list of 3 integers, but if we have some more complex objects, it may be a problem. So we may try to return a view, something that is actually synchronized with what happens to the triangle, okay, but doesn't allow us to modify it unless we make a copy. This is a bit better, because we don't have to make a copy unless we really need it, okay? And we'll see a trick to do that with NumPy in some slides. Third possibility is probably change the API. So this is very general, okay? You can do whatever you want with that, but do you really need to access such information about triangle? All the vertices like this? Maybe you do, maybe you don't. If you don't, then change the API. It's just better. It avoids a lot of problems. So, what about the Python object model? I'm not going into the details of the Python implementation of the object. So, for example, I leave completely out the descriptors from this discussion because I'm more focused on the memory occupation. interpreter for some stuff which we don't care about right now. And the built-in objects give correct results because that's in the documentation, and if they do not, it's a bug, we can point that out. But first, still get size of is fooled by this. And we can also see that get size of automatically considers some of the slots, okay? But it doesn't consider attributes. So the dict is basically ignored. Of course, an object with 1,000 attributes is just an exercise in bad design. So this is not a problem, but we have to consider that somewhat the slots are taken into account and that the dictionary is not. So if we want to implement the size of attribute method, we have to be extra clever to do the right thing. And we start with the integers, about the internals of implementation performance details. We had seen in a couple of slides ago that 10,000 integers take 240,000 bytes. And yes, one integer takes 24 bytes in Python. And for example, on a 64-bit Intel machine like this one, C-long takes 64 bits, which is 8 bytes. The thing is, an integer in Python is a full-fledged object. It's not just a box in your stack, okay? It's something more. And here we do not consider the long data type that expands and it's more complex. This is just a simple integer, okay? It's implemented like this. This is just the head of all Python objects, which contains this field for reference counting, or brefcount, and a pointer to the base class, okay? So all C Python objects have that. And then the integer adds the ob-ival field, which is a long, okay? So that's where your number is stored. So instead of having just that field, you have all the Python object machinery around that. So the thing is that although they are actually larger than C integers, Python integers are still small entities, like 24 bytes, as I said. And the cost of individually mallocing each integer would be too much, both from the CPU point of view and from a memory user point of view. You know that malloc to work needs to keep basically lists of free blocks, so there is some infrastructure that works bad with very small objects. Okay, it's rather efficient if you malloc large chunks of data, but it's not if you just allocate small numbers. So for example, in C++, there are a lot of techniques to make allocators for small objects, because usually if you're using C++, this kind of things matter. And since this thing is very widely used because integers are popular data type, Python also does some optimization regarding the integers, which are puny objects actually. And this is how they are implemented, in fact, that the memory. We have a small area where we statically allocate some small integers from -5 to 256 something, or maybe 55, but still we have an array where we just put the integers, okay? And the other integers are kept in this other structure. We have a linked list of block, basically, and we do not malloc integers, we just take slots in that structure, okay? So, for example, these are allocated integers, 3 and 7, which is, 324 and 3672. Each of them has some references, so this is used seven times, shared by 7 attributes, something like that, this by 3. And these are just integers. So you have a list which contains pointers, for example, to these integers, to these memory locations, this and that, okay? The free part here, we have a free list of allocated memory, and the OB type pointer is overloaded. That's basically a hack, and it points to the next free integer, okay? So we have a free list pointer, and when we want an integer, a new integer, we get here, we use that, and we take its OB type pointer, which points to the next integer, okay? Next free space for an integer. And when we deallocate an integer, we just put it back on the free list, okay? Of course, we can have more than one pi block, which are all linked, and these are, okay? That's it. So in fact, when you create or destroy integers, so you don't destroy integers, they are just garbage collected, you don't call malloc, you don't call free, usually. Of course, you may have to call that to allocate another large chunk of, I think, 1,000 integers, but usually you don't do that. So that is rather efficient, in fact. And so, not only that the memory usage for integers is a bit more complex than you expect, also the implementation. Because you know, in Python we have signed integers. And signed integers in C have issues, in the sense that unsigned numbers do not have problems, because they have this modulo arithmetic, so they don't overflow, they don't underflow, they just wrap around. So the largest, if you add 1 to the largest unsigned integers, you get 0, okay? If you do that to an integer, you have undefined behavior, okay? So we don't want our interpreter to go into undefined behavior, you know, the whole nose demon from the nose flying thing, which is rather unpleasant, especially in your beautiful Django website, maybe your users as well, I don't know. So you don't want Python to do that, and instead, for example, just the sum is done in unsigned in the unsigned domain, okay? So this is the actual implementation of the addition of two integers, which you may be led to think it's just a CPU instruction. In fact, it's something more complex. You have to get the integer from the Python integer, the long from the Python integer. Then you do the casts, which are usually free in the compiler implementation, but see, you do that, then you check that you didn't actually overflow, okay, because this is not an error, this can go bad, but you may recognize that you would have had an overflow if you did that into signed arithmetic. So in this case, you just, this went well and you return the integer, so more code. This didn't go well, and you have to switch to long numbers, long Python numbers, okay? But things can get worse. For example, with multiplication, it's a bit painful to check whether multiplying two numbers give you overflow. Not really, it is. I've been doing that once. We were doing a static analyzer and we had to do checks about overflow, underflow, and it's painful. It's not nice to do. So in Python, in fact, floating point arithmetic is used to do that. Basically you multiply the two integers, and you also multiply doubles created from the integers, and it's checked that everything works fine. So if you expect, for example, that just multiplying two integers doesn't involve your floating point unit, that's not true. It does that, which is efficient, by the way. It's probably most efficient than just checking the bounds by hand, but you have to consider this, okay? So there is a lot of magic going on here. Floats, well, they work actually like integers. Of course, we don't have a small float array because it wouldn't make sense, you know. But still we have the whole blocks thing, so we don't malloc and free each float individually. We just work with blocks. The operations are done according to the C platform semantics, which usually is the IEEE semantics and everything as well. And plus we don't have the faulty algorithm that the guys from PHP and Java had, which made everything crash if the wrong numeric literal was provided to the compiler, but that's another story. And so, for example, when you do something like this, some code is involved. You are creating integers. You are taking the double from the float, sorry. You're taking the double from the floats, multiplying the floats, creating another float. So it's a bit more involved than you would think. Luckily enough, NumPy solves this as well. And now we go to containers. The first container we analyze is list, which is implemented as an array of pointers to Py objects, of course. So, about complexity, get set is 01 is good, and append is also amortize 01, so it's efficient. You can append to the end of the list, which is convenient. You should not insert it at the beginning or in the middle of the list. If your algorithm does that, you have a big problem. It's not a Python problem, it's your algorithm's problem, okay? You must not insert stuff inside the arrays, okay? Because you have to copy stuff. Instead, you can append at the end. But the thing is that if you look at this kind of code, you see that there is a lot of, this kind of object, there is a lot of indirection. So here, this box here contains the actual definition of the list, which is a Python object. So opref count, optype, and you know, the size, because this is variable size Python object. That's nice. And here we have opItem, which is actually pointed to this array of pointers to Python objects. And each of this pointer actually points to a Python object. So, for example, this is very sparse in memory, you know. This may be allocated in a completely different area from this and that. So caching, I don't know, sometimes may be a problem, okay? You have to keep that in mind. The list is very nice to use, but it's not implemented in the most efficient way. For example, if you have just numbers, you may want to use an array, a Python array, or a NumPy array, better still, okay? And then there are dictionaries, which are probably my favorite data structure in Python, which are used everywhere. It's probably the most important single thing in Python. Objects are implemented with arrays. We have seen the dict object, the dict attribute. And most algorithms that we want to implement in Python may be using a dictionary somewhere, because it's very fast. It's definitely not a textbook implementation. It's a beautiful, highly optimized implementation. So you won't see linked list hash tables here. Open addressing is done, which is more memory friendly actually. And complexity is standard, of course. So we have get set in amortizer 1 stuff. And this is the actual implementation. We have a dictionary. This is Python 2. This was recently changed in the latest Python 3 implementation. But in Python 2 we still have this structure with a hash, a key, and the value. Okay? And there are 3 kind of keys. The unused keys with both me key and me value to null, and active, which typically have me key, which is neither null nor dummy, and me value, which is not dummy, not null, and dummy keys that are actually have me key, which is dummy. Okay. So the idea is that me hash contains the hash, and Python uses very simple hashing function for strings and integers, which is something that textbooks do not advise, but they are wrong, because although theory says something, in practice this works better. Okay? For example, the hash of an integer is just an integer. Okay? Sorry?
You have a long integer.
Yep, right. And we also have a simple probing function. Okay? So simple stuff which is faster. A Python entry, by the way, is 24 bytes, I think. Something like that. If you just do the math on a regular Intel-like computer, that's 24 bytes. This is how the probe works. I wouldn't go into that, but basically you have an array inside the dictionary which contains all the dict entries, okay? And we don't have linked nodes here. When we want to get an element, we just compute the hash of the key and we get to the breakpoint. And if the hash, if the key is actually a key, we get the value. Otherwise, we have a function that tells us where the next in the chain should be, and that's about it. And the function, as you can see, is very, very simple. Okay, so that's all I have to say about that. And we come to the actual definition of the integer, of the dictionary here, and we have some fields here which are not actually important from our perspective. The thing is that a dictionary contains a small table, so small dictionary are optimized in the way they do not have to allocate the table, the actual hash table, outside the dictionary. It's just there. But the thing is also that each dictionary is a very large object. Okay? So it's about 280 bytes each single dictionary. Because of this bydict mean size, it's 8 plus all the other fields, we have a large object. And it stays large, okay, even if we actually I don't know, use another lookup table like dictionary grows, we still pay that, okay, always pay that. But this is good because we don't have to allocate memory every time, which is expensive. So, to give you an idea, as I said, 180 bytes on a 64-bit Intel machine, and a lot of Python objects have dictionaries. So it's not unusual that a very large part of your memory goes because of dictionaries. And this is the way in Python it's common to represent a graph, okay? So a dictionary with a list of nodes. So this means that there is an edge from node A to node B. Okay? This kind of structure has some issues, for example, because you may, if you want to know if there is an edge, you may have to make a no-end search here, or you have to keep that sorted so you can just do binary searches, but still this has issues. So for example, NetworkX, which is a very popular library for network graph manipulation in Python, uses a structure that is done like this. So dictionary of dictionaries, okay? And this is very efficient, for example, to test whether there is a given edge. This list here is used because you can also give labels to edges, which is very, very nice to do if you are doing like social network analysis, complex network analysis. It's nice. But the thing is that this small dictionary takes, this small dictionary takes 2,000 bytes, that is 2.5 kilobytes of memory, 6 elements, okay? And as I used larger networks, I found out that a simple 1 million node network with network X is 5 gigabytes of memory, okay? Just to be there. It's a huge amount of memory, especially if you consider that if you implement the whole thing as a sparse matrix, a sparse adjacency matrix of the network, it's less than 2 megabytes, okay? So you have to understand what you're doing. This is very convenient to use. You have a very beautiful interface. You can do a lot of interesting stuff with it, but it's not going to scale, not at all, okay? And I was a bit surprised at the implementation of a graph in the probably most popular library for graph manipulation in Python is so inefficient. Okay, it makes sense. Still, I had to switch to something else because of that. And then there are the tuples, which is the last data structure in Python. Some opinions here. Wesley Chan, for example, advocates that we should not consider a tuple as a data structure, at least not as a data structure to manipulate data. He suggests these three uses, like composite dictionary keys or individual entities, okay, or just to get data to and from functions. That's it. And this is the overhead of tuple, okay? It's not a lot, but if you want to have a list of tuples, a list of a lot of tuples, this is going to be bad, okay? So every layer of indirection, you pay for that. And since we have seen that getSizeOf doesn't give you the whole picture, because this is not the size actually used here. That is the size of the tuple. The size for the two strings is not here, okay? We want to actually know how large are our objects, okay? So we can use getSizeOf, but it doesn't work like we expect it to. We can use recursive recipe. I think that this link here is for the version for Python 3, but you can adapt it to Python 2 as well. Or we can use this library, Pimpler, which provides module sizeOf. We can install it just from the G shop, and it just gives the right total amount of memory, okay? So this here contains the two integers. This is a slotted point, okay? This is done with slots, and this is a named tuple, which means slots. And this is all points, so you can see the actual difference of the whole thing. Okay. This is with a sizeOf, and this is with getSizeOf. This is the real memory used for this one, for O. The size of memory we see that is used by the version with named tuples is actually somewhat a bug. I included that here because I was very surprised when I found that out. So a sizeOf does some inspection of your objects to try to figure out actually how large is that. It has to navigate through all the numbers, through all the attributes, okay? There is a problem. Named tuples do not have a dictionary, but they have a dunder property, because sometimes it's very interesting to get that. And there is code from this property that when you require for it, it gives you an order dict with all the stuff inside, okay? So the memory was not used until I measured it. That's quantum mechanics, okay? But so this kind of measures are, you have to be careful because of that, okay? That's not a problem when you know that, okay? So that was the reason, because I just showed the internals, because that's the extra memory you're using, okay? If somebody else tells you otherwise, then he is wrong. Implementation doesn't lie, code doesn't lie, unless it's just obfuscated to the point you don't want to have anything to do with it. So, putting all together, Python code structures are very useful and powerful. I love them. Really, when I have to work with, for example, Java, the thing I miss the most is the ease you have to work with basic data structures in Python. That is what I like most, probably. Well, no, I like that a lot. And they are built for ease of use, plus some performance constraints, like the super fast dictionary implementation. That is just wonderful, okay? But usually we want things to be easy to use, okay? And as object-oriented programmers, we want to provide interfaces that are easy to use. The thing that each nested structure forces some indirection, okay? So you have these pointer chains that you have to follow. Well, your CPU has to, unless you're doing low-level debugging. In that case, you are doing that. But let's assume it's just your CPU work, which is a problem sometimes, okay? You have no memory locality, okay? Maybe. So you have to consider that. Sometimes the solution is just simple. You use NumPy. NumPy objects are different because they are, I think they have a very beautiful interface, because they are nice to use. They provide all the methods you expect them to have, and NumPy provides the function that you would like to use. So that is nice. But actual memory usage is just here. They have somewhat inside their guts a memory structure, which often is just a plain chunk of memory. Sometimes not. They have holes. For example, if you do slicing and this stuff, you may have holes and it's not as nice. But you can also ask for a NumPy array with contiguous memory. You can always have contiguous memory. When you have contiguous memory, you decrease the overhead, and you can pass that to C function or whatever expected C buffer, okay? So that is both memory efficient and may be the basis for your later optimizations. Plus you have all the Python object-oriented stuff upon that. But typically, if you use large matrices, like you do if you do scientific computation, the overhead is small. It's very small. And there are also some tricks. For example, when you copy and de-erase, you may share the memory, unless you don't want to. Okay? So, you can explicitly want a full copy, a deep copy with memory and all, or you can have sharing, which is more efficient. You can require a view, okay, which just provides a different access pattern to your memory, or even the same access pattern. And this is very efficient because you're not copying memory, you're just creating small objects. Plus, you can do this, which is a trick I discovered just not a long time ago. So, you can make a view of a NumPy array, and you can switch a flag here and say it's not writable. So you can give it to coded side, and they cannot modify it unless they either copy or they switch this flag. So it's what doesn't happen is that you just modify something that you shouldn't modify. Okay, as we are all adults, so if we want to do modification, I don't want the language to forbid me from doing stuff. But I don't mind if stuff I wouldn't want to be usually doing is harder, a tiny bit harder. I can also require a copy or flip this flag. So this is nice. If your triangle had inside a NumPy array of numbers, you could use this trick. You make a view, which is fast, and you switch the flag. Well, to be completely sincere, for a list of just 3 numbers, probably that is not so fast compared to copying the list. But in general, I choose as a simple example. That doesn't mean that the general idea is wrong. And now we get to profiling. So, profiling versus benchmarking. Profiling is a dynamic program analysis technique, error, to measure space, frequency or duration of function calls or instruction of whatever you want. So, it's one program. You just measure your program. You measure parts of your program against other parts of your programs. Okay? The most typical profiling you do is just count function call and see how much time is spent in function calls. Benchmarking usually implies that you have a set of programs, where a non-empty set of programs and non-singleton set of programs. You have at least 2 programs that you want to compare. Sometimes you use benchmarking to say just see how fast it is. I'm not very friendly towards benchmarking because it tends to lead you astray. Okay? You see numbers, but often they are relative numbers. They are absolute numbers. It's not relative. You do not really know how fast your program should be. You always have the idea that you could make it faster. But no. You don't have to do that unless you know, because your client called you, and it's too slow. It doesn't answer the request fast enough. So if you have a problem, you must know that. Then you can benchmark it, you can profile it, whatever you want. But you must know you have a problem. You don't have to just think that you could be faster. Okay? So I am a bit against benchmarking, especially one program benchmarking, which is not even benchmarking, but still. You may want to compare your program to another program, and you may see that the other program does the same things in 1/10 of the time. Then maybe you want to consider optimization. So you need profiling. You always need profiling. You can't optimize anything without profiling, unless you wrote very naive code. Okay? If you have, sometimes you can do that, but most of the times you can't. It's surprising the amount of misdirection that our progressed experience gives us when we want to optimize a program. Okay? Profiling tells us where to look. So, profiling says where is the problem, and benchmarking sometimes answers to the question, is there a problem? And that's about it. So, about benchmarking, we can do manual solution. For example, MATLAB uses tick-tock. Okay? You just tick, then have a statement and talk. I believe something like that is also in EuroPython, but still. Then there is a time-it module. We can measure pretty effectively how much time goes to execute some statement. But I think that since I have EuroPython, I'm not using anything else to benchmark something, unless it's not Python. Because I can just use this magic, time it, statement, and then it works. Okay? And it also has automatically access to stuff you may have defined before. Okay? So it's not like you have to do some small scripts to actually benchmark the scripts, to time the script, because you have some setup. You have just your shell, you're working there, and you just call time it, and you can also call it in cell format. So here you have the statement, the setup statement, and here you have the actual code that is benchmarked. I didn't remember that function are fast at lambdas. I was under the opinion that the performance difference was removed, but probably it's not that, or this is the classical problem with benchmark. Okay, this function does not a lot of code, so there can be a lot of errors in measurement. So benchmarks lie a lot, and you don't want to trust them because of that. Profiling is different. When you want to profile something, you typically have to change the code. You have to instrument the code. And this is bad in the sense that profiling cannot be used to measure performance because it changes the code that is running. Okay? And this is how you do it with the cprofile module. Okay? You can run a statement, and in this case you save the results to this file. You can also call Python with mcprofile, this option here, and the script you want to profile also works. And of course you can also do that from inside EuroPython with the prun command, which is, as always, the most convenient way to do it, usually. You have options to the prun command so that you can put the output both on the standard output and in a file, just on the standard output. If the execution is large, I typically want it in a file outside, and later I can examine that with pstats. Okay? So this is roughly what you get from profiling a bunch of code. Okay? You know the number of function calls that are made, primitive calls, the number of seconds it took the execution, but that is modified by the fact that you are running the profiler itself. And here I required the statistics to be sorted by cumulative time, and just want the top 9 here. That's the API of pstats. So the total time is the time that is spent inside a function, regardless of the functions called inside the function itself. So if you have function A, which does something, and then calls function B, cumulative time contains the time spent by the instruction before the call to B and by the call to B. The total time just measures the code before the call to B. So sometimes you want to know the global time spent in the part of your program, then you're interested into cumulative time. That typically leads you to the part of the program where 90% of the time is spent. Okay? If you want to know how much time is spent inside a function, because for example you're not interested into subfunction you call because you know how they behave, then just regular time is the thing to go. So here we can see that these functions here are larger scope functions. This is the main function, okay? And we can see that most computational time is spent there, okay? And these other methods and functions are just very high-level functions that are called from the outside. So they are not very interesting, and we can also see that they are called just one time. So this is a pretty clear indication that here we are just getting into the guts of our program. That's just it. The first interesting part is this. Apparently this method here, readPost, is what really takes the most time, okay? Inside it, most time is spent. It's called a lot of times, but we may want to optimize that method because of that, okay? If we just make this method twice as fast, our program is almost twice as fast. The thing is that the total time spent inside this is small. It's just 53 seconds over 600 and some. So this tells us we don't have to actually optimize the code of readPost. We have to see inside readPost to get the code that is responsible for the longest time of the computation. So this is a bit how you navigate with profiling. And in this other example, we just order things for the time and not the cumulative time. Okay, and we see that actually this private method here is just where most time is spent. just directly in that method. Okay? So, if we optimize this, oh, that's good. It's just 1/3 of the program. We can do a whole lot of optimization because, for example, if we do that 10 times faster, our program is going to run in 2/3 time. Okay, so it's not great, but still it's our best option. By the way, I tried everything on this. I tried Python, I tried whatever I could. Performance cannot be improved, maybe 10%. So I'm not going to consider that. And there is a thing which is very useful, which is line profiler. As I said, we can see the difference between cumulative time and the actual time span. And this gives us an indication of the methods that we actually want to optimize. But it's still very rough. And in Python we have better tools. I love line profilers. Okay? You can just install that from the cheese shop, and you can work with that in two ways. First, you can take your source code and use the profile decorator on the methods that you actually want to profile. Then you run the program, and you can access the results like this. Okay, line profiler is module, and you can get to that. Of course, you can use EuroPython in a more convenient way, like this. So, for example, we have a list, we shuffle it, we load this extension for EuroPython, and we can LP run the code. The F option is used to indicate which functions we want to actually profile. And we get this. This function is basically a stupid insertion sort I found on Stack Trace, something like that. Stack Overflow maybe, I don't remember, but still. This is the function, okay? And I run the function here on the list, and I specified that. Since I put in a module, I had to use the fully qualified name, okay? And I get line by line, I am told how much time is spent, how many times that point in the program is hit. We had 100 element list, so we get here 100 times because it's 4. Okay, that's very bad, but still bad code. But it's not the point here. We know the time spent here. We know how much each time we got there, how much time went, and the percentage of time that is that. So, for example, we know that the inner while loop takes the most time here, okay, which was something we actually expected, but that's pretty simple code. Of course, when you change the size of your inputs, you may have some differences, like all this has almost no weight if we make a larger list. I think this is a 10,000 size list. See, this module is beautiful because it gives you so much information exactly in the way you need it, because you have the function you want to optimize, and it actually tells you which line is the problem. Of course, you have to know how to fix it, but okay, we can do better than that. And we can switch to memory profiling, which is another big thing. We don't have a standard memory profiler like C profiler is. So there are several options. We have object graph, which creates a graph of references and back references. Okay? And you can also navigate that. There is Melia, which works a bit like C profile and P stat. So you just instrument the code. It measures how things work and then dumps them to a file, and you can load the file and check it out. And then there is Pampler, which is especially useful for memory leaks. You can make snapshots of your code and see what changed between two snapshots. But time is a tyrant, so we have to just see a few of them. For example, object graph. These examples come from the main site, so very simple. we have this thing here, an empty list put in X, and we have a very stupid list epsilon or Y if you don't like Greek, which contains X and a list containing X and a dictionary with an attribute X containing X. It looks like, well, input object graph, okay, and we can show ref, called the show ref method, starting from this object here. This is a list of starting object when we want to compute the whole thing, and a file where we want to save that. We need graph.viz to do that, and the file contains this beautiful image. We see here the list, this list, which is referenced into a dictionary in another list, and it contains a dictionary, a list, and an item, which is also contained by the list and the dictionary. Plus, we have an attribute X in the dictionary. So we can use that to see how a memory layout is. And in the other part of the slide here, we have the back references. So we switched basically the direction of these edges, and these arrows go from here to here, and here the arrow goes from here to here. So here we know that this list, which is this one here, was referenced in these three objects. Okay? So for example, you have an object that you should have seen destroyed, but somebody's still referencing it. You get it, you call object graph on that, and you see whoever it references that object. Okay? That's it. That's the idea. Of course, when you have a complex piece of software, things go like this, which is quite a bit less useful. Luckily enough, if you are not a capitalist Mac-loving user, you have X dot. Well, a working X dot. I didn't manage to have X dot working. And with X dot you can more easily interactively navigate the graph. No, actually I think if you use X11, XOR, something like that, you can have X dot working. It was just a joke. So the thing is that you can just expand the part of your graph that you're interested to, so you have the big picture of how the objects are related one to the other, and you can just zoom where you want. The other philosophy that we have is that of Melia here, and we just load the dump of memory, and we can, for example, print a summary, and we get something like what we had for CPU profiling. Okay, so we know that strings here take 58% of the total memory size, and are 46% of the number of objects. And dictionary also have a very large part of the memory. There are APIs in Melia where you can, for example, omit the dictionary inside the objects, because once you figure out that dictionaries inside the object take a lot of space, well, then you have to either decide whether to slot something or whether it's fine by you and leave things as they are and just see other problems. Okay, so that dictionaries are not measured anymore. Once I was using G-Event, and it was beautiful, and I found out that a third of my memory was used by frames, call frames, because I didn't explicitly destroy a closure that I created in some part. So sometimes this helps. So how can I get faster? Well, PyPy, of course. For floating point computation, we can use NumPy with PyPy maybe. And we can also call other libraries. There is a huge environment of Python scientific fast libraries, like for example pandas, which can be described as R in Python. You know, the ugly semi-functional language used by statisticians. Well, pandas give you the functionality, it's faster, and it's Python. So you win on, well, just win. And then there is weave, so you can embed, if you have pointer env, for example, you can just embed some C++, which works well for code obfuscation as well. So this this thing here lets you compile the C++ piece of code here, which is a string here, and we say what variables we want it to be passed to this chunk of code that is compiled and called and whatever. So for example, number of rows of the matrix, number of column, the area of memory when we want to put data here, and the actual matrix and the the vector. And you can just run it. First time it's compiled, and then you go. Thing is, NumPy is faster, actually. So NumPy takes, well, NumPy is, sometimes it's Fortran, so you win. Especially because you don't have to code that. So that is 2 milliseconds, that is 19 milliseconds. This example comes from this book, where some code was compared. The actual problem is that I wasn't able to reproduce these numbers. So, for example, we've just 1.6 times the NumPy version, but I got so much. The NumPy version was so much faster. I believe that their example, these numbers may be a bit old. Still, the thing is that they claim that NumPy dot can be as fast as a cache-friendly Fortran program. So, but this is believable because underneath NumPy is probably a cache-friendly, high optimized by 40 years of improvement Fortran piece of code, or maybe a C piece of code made to be as fast as a blah 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 Fortran piece of code. So then there is Triton, which I'm going to skip, but the thing is, this is a huge tool which sometimes can save your day. You can do some interpretation with NumPy, you can make it work with C and C++, you can declare buffers even on the stack. So it may give you options that Python doesn't give you, and it's very easy to call from Python. For example, here we define we declare some types which are two-dimensional matrices, and that can be really fast sometimes. And plus you can make objects without Python overhead, because the methods of this object are not available from Python, so they do not have to provide Python semantics, create stack frames, all of that. So they may be the right choice. Plus there are some gems. I was using Mongo to process some numbers, and I wanted to do some processing with NumPy, actually. And thing is, I could have used PyMongo, which is nice, if you like Mongo. But it was a bit slow. I just needed to load chunks of code and to process them in NumPy. This example comes from the Monary website. It's not the code I use actually, but the idea is this: it can query the Monary, the MongoDB, and here you get a matrix, a NumPy matrix with columns with these attributes, with this name. There was a data structure in Mongo with these attributes here. Well, a collection of of rows with these things, and you just get a NumPy matrix, and it's super fast. Okay, this is the performance of Monary, and this is the performance of PyMongo. So, because that just opens the connection and directly writes to a C buffer inside the NumPy array. So, whenever you can use non-nested memory and efficiently constructed objects, you have huge performance improvements. And I think that's about how much I wanted to bore you this morning. Thanks.
Thank you, Enrico. Okay, we have some questions.
Could you please explain a little bit why the hell does name tuple take so much memory? Like you mentioned like 500 bytes, right? Or it's just a side effect of deep size like measurement?
So you want me to go to the tuple slide here, which is the only one without the actual implementation, so it's going to be a bit hard. So you are asking why a tuple takes that amount of memory, right? Name tuple. So
Heisenberg memory.
yeah. Oh, okay. Yep. So sorry, I got the question wrong. Here. The thing is this. Name tuple, if you just open up the implementation, you can see that although name tuple does not have a dictionary attribute where the attributes that you declare are placed, they have a dictionary, a dunder dict dunder property. So if you explicitly require the dictionary, a dictionary is created. Okay, this is clear? So the dictionary is not there unless you require it. If you require it, it's created. But the code that measures the Python objects has no special case for name tuples. Okay, so they just try to see if there is a dictionary and measure it. The thing is that if you require for a dictionary, you get it. So it's measured. Probably the fix would be to have a special case so that for named tuples, dictionary is not queried at all. So it's not created and it's not measured. By the way, when you create it, it's not added to the named tuple. It's just some commodity function if you want to do, I don't know what you want to do. Okay? No, maybe it's added. I have to check it out. However, that's about it.
So I have two small comments. One is about memory profiling. I very much recommend Memory Profiler, which is just like Line Profiler, but for memory.
Okay.
And it's very cool, so it works well. And also you can use PSUtil if you want to measure yourself the memory, the occupation memory by your operating system. And then there is another user case that actually we have, because we run our computation on a cluster, and in that situation you cannot use profile, because the profile works if you have one process.
Yep.
But if your Python process is spawning 100 different processes, you cannot measure profile the other one. So what we did was just to write a context manager, which is able to measure on the enter and the exit, measure the time and the memory.
Yep.
And then we save this on a database. So the idea here is not to have run once profiling, but you have a persistent instrumentation on your code.
Yep.
Of course, you don't put this in an inner loop, but I mean, outside. And so you know always how much time is spent in your, let's say, hotspots. And if you change something, so you have a new branch, you can immediately see if there are regressions, if you are occupying more memory, etc., etc.
That's beautiful.
I don't know if there are, this was custom made, I don't know if there are on the market tools like that.
And how complex is to put out?
It's very easy to implement, so I don't need that. Just wanted to say that there is also this option to write yourself your own tool. It's very easy. It's something like 30 lines, 50 lines of code. It's not much.
Thanks.
Hi, thanks for your talk. extremely interesting. I'm new to Python and it's really cool to see how the internals hang together. I'm going to be a bit of a devil's advocate. If you are this concerned about memory profiling, memory footprint, should you even be using Python? Is it actually the right tool for what you're trying to achieve when we take into account good enough is good enough and Python is a tool for getting things done approach?
Well, I actually think it is. Let me explain. If you design things carefully, Python has a small memory footprint. It's not Java. Java is huge and, well, at least I do not know how to control it, in the sense that sometimes it takes huge loads of memory and I can't do anything about it, and if I limit the memory then things start to crash. Python doesn't do that. As long as I keep things under control, I can manage to have a relatively small memory footprint. Like, for example, I don't have integers going around, but I try to keep them all in matrices. Not a lot of layers of abstractions. You don't get to the individual integer, something like that. And the thing is that to do something as fast in C++, well, I can do that, but it's so much more expensive. And I usually prefer to try at least the Python version first, see whether pandas, NumPy, whatever can do. Otherwise I can switch to Python, and maybe if all that doesn't work, I can create some low-level C object and work with that. As always, with clever APIs and without exposing and creating lots of Python objects.
So as a comment, there are two other ways that you can use Python to store data more efficiently. One is the array module. You have homogeneous data, but don't want to worry about any of the math. And the other is to use the C-types structure for heterogeneous data. And I've used that nicely for having some stuff where I just wanted to have XYZ, name, and a few other things in one data structure repeated 1,000 times.
I agree. Thanks.
Okay, so while I move the mic, I ask you, if you have considered like Number, and did you take a look at that, and do you know, are you aware of this new stuff coming out?
New stuff? No, I'm conservative.
Okay, don't consider.
Sorry, I'll look into that.
Hello, first great talk. It's hard to see the different levels between high-level Python and the implementation. Just to answer this gentleman about the idea of implementing in C, in my former company we built a 3D modeler in Python. So the main goal was to have this smooth curve between Python, which was really easy to build but slow. And then we went to better modules like array, then to NumPy, then to Cython. But each time we had this exit strategy and move lower and lower. So it worked quite well because it allowed us to experiment with a lot of stuff. So this is definitely doable. I mean, you can be really, really fast, and more times than not we realize that changing the architecture was the right thing to do. And it was possible in Python. It would have been possible in another language because the number of lines to modify would have been too high and would have been too risky. So just this. But my real question would be, in your example, you take triangles and point. And I was just wondering what would be the right way to do that from a performance perspective in Python, using not cheating, I mean not going into C directly. How would you do that? I mean, like the triangle and all this stuff.
First of all, I want to say thank you for the first part of your questions, because I completely agree with you, and thank you for sharing your experience on that. My answers to this triangle thing is I don't believe in perfect APIs. That is to say, your question is something like, okay, what's the right interface for a triangle? I have no clue. Depends on what you have to do with it. Okay? So, if we have a use case, I think we can design an API that is fast, reasonably efficient, reasonably easy to use, depending on the extra constraint of our thing. But just to design a triangle interface looks a bit like a textbook exercise. And the more I try to make it general, probably, the more it's going to be slow. Or I'm going to expose internal details, which sometimes is what I want to do. Okay? So, for example, some stuff, I don't know, like in Matplotlib, for example, if you want to plot a triangle, if I'm correct, you just pass an array of 3 points, something like that. Am I correct? Okay, so for example, the interface to draw a triangle is just a list, an iterable of points, well, 2 iterables of coordinates perhaps. So if I want to use that, for example, to plot my triangles, I need something like that. Or I have to make such large API where the code is embedded in my triangle objects. So I have self-drawing triangles, which is something I do not know if I want, okay? But maybe if I have to give this API in the hands of some, I don't know, a mathematician that wants to interactively do geometry, then it's the right thing to do, maybe. Because performance is not that important. Design, well, it's more convenient because he has to code it from the command line. And so it's the right thing. But if I want my triangle to be, I don't know, the triangle of the GPU and the things you do, well, you probably don't even have an interface. I don't know. You maybe have just a chunk of bits. So really depends, in my opinion. Sorry to having not answered your question, hopefully in a very elegant way. Hopefully.
Okay, so I have a question. With a node, the number module, it's a just-in-time compiler that lets you annotate functions and decorating them, and it compiles to LLVM and giving much performance boosts. And my question is, your talk is mostly about optimization and performance measuring, about computation, and most of the time you have to build up your own data structures, or it's always a kind of recipe to, it's not a static solution that it will work, and if it often clashes with another type of optimization about I/O bottlenecks and so on. So how do you try to match those type of, I mean, pandas, for example, have many built-ins to store stuff that you are using, but many times it's difficult to like just improve computation without messing up with I/O stuff and vice versa. What's your feeling about that?
Yep, that's one of the main problem I think in Python, because especially we have all the GIL issues. So sometimes you want to, I don't know, I don't like threaded code, but sometimes it looks like the right solution if it's just architecturally sound without sharing and all that. So when you have to read and write and do CPU stuff and all that in the same process, I know it's difficult, especially because maybe you want to use some kind of database that has some kind of latency, and you have to convert the data. That's a huge problem, and you have to evaluate very carefully. For example, sometimes I use PyTables, or the other model, I think it's H5Py, something like that, which doesn't provide an interface that is as rich, but it looks more like NumPy matrices, and sometimes that works, okay, for example, but sometimes Mongo or something like that is just faster. That depends on what you have to actually do. And for example, for Mongo, I find that module that greatly simplifies the task of getting data from the DB, because you have seen it's almost 10 times faster. So that can really make the difference, okay? Because 3 seconds you get the data, then you process it instead of 80 seconds, okay? So that may be the solution. Sometimes it's not. Sometimes you have to work a lot with the disk, because you have so much data you can hope to put it in memory. Sometimes you may make sacrifices and try to fit everything in memory, maybe by choosing less efficient structures, but that allow you to keep everything in memory, because you are reducing pointers and all that. So it really depends on what you have to do, in my opinion, at least.
Thank you. So we have 1 minute, then we have the coffee break, so it's the last question.
Thank you for those low-level explanations. I would like to ask even lower-level question.
Oh.
The 4 GB limit.
Yeah.
Which operating system version, processor, system combination is possible to get more than 4 GB in one process?
I believe that nowadays, with 64 CPU processors, I was able to have like 10 gigabytes Python processes.
Worked.
Yeah?
Oh, maybe I'm just a Windows user.
No, I didn't use.
Okay.
I didn't use Windows.
I'll ask Microsoft.
To be completely honest, I have to say that sometimes Mac OS X does something very strange. When you have very large processes, sometimes it hangs the whole system. Not in the sense that it crashes, but in the sense that it becomes very slow. So I think there is something wrong with the trashing, caching, that kind of stuff. So I just open Linux virtual machine and then it works. Not joking. I did that. I actually did that. So probably if you want to do that stuff, you know what you have to do to use.
So thank you so much, Enrico.